Welcome back, everyone. Today's explanator is essentially a masterclass on the ultimate rules that govern, well, literally everything. We are talking about the laws of thermodynamics. Whether you're boiling water for your morning coffee, cruising down the highway in your car, or studying the life cycle of distant stars, these are the absolute fundamental principles dictating exactly how energy is transferred, transformed, and conserved across the entire universe. So grab your notebooks because we're about to decode the actual operating system of the cosmos itself. Here is our agenda for today's deep dive. First up, the vocabulary of heat. Then, the history journey. After that, we'll get into the main event, the 4 laws explained. Then we'll tackle the math and common mistakes, and we'll wrap it all up with thermodynamics in the real world. Okay, let's kick things off with a question. Imagine you drop a big box of Lego bricks on the floor. Why do they always scatter into a giant foot-destroying mess everywhere? Why don't they ever just naturally fall perfectly into the shape of a magnificent castle? You know, it seems like kind of a silly question, but the physics behind why nature prefers scattering over perfect assembly is actually the golden key to understanding energy. We're going to answer this using a concept called entropy in just a bit. All right, section 1, the vocabulary of heat. Whenever we talk about thermodynamics, we always have to draw a boundary around what exactly it is we're studying. We call that specific slice of the universe the system. That could be your cup of hot tea, a car engine, or even a single human cell. Absolutely everything else outside of that boundary, that's called the surroundings. The entire basis of this science really just comes down to looking at the relationship and the energy exchange between a system and its surroundings. To make this super concrete, think of it like a lunchbox. An open system allows both matter and energy to move in and out. It's like an open lunchbox where you can easily take food out and the heat can freely escape into the air. A closed system is like a perfectly sealed lunchbox. The food is stuck inside, but it can absolutely still get warm or cold. And finally, an isolated system is like a perfect, totally idealized thermos. It exchanges neither food nor heat with the outside world. Now, remember those dropped Legos? This brings us to a massively important definition, entropy. A lot of people just describe entropy as messiness or disorder, but actually, scratch that. As a physics teacher, I want you to think of it much more precisely as a measure of energy dispersal. It's really about the number of possible microscopic arrangements in a system. I mean, think about it. There are millions of ways for Legos to be scattered on the floor, but only a very specific few ways for them to be a castle. Nature just naturally moves toward greater energy dispersal, which is exactly why your Legos always stay scattered. Oh, and real quick before we move on, we've got to clear out probably the biggest misconception beginners have. Heat and temperature are not the same thing. They're just not. Temperature is a measurement that relates to the average kinetic energy of the particles inside an object. Heat, on the other hand, is the actual energy in transit. It's the energy being transferred from one object to another specifically because of a temperature difference. So heat is an action. It's not a static property that an object just permanently holds onto. Moving right along to section 2, the history journey. Interestingly enough, these laws weren't just cooked up by one person overnight in a lab. They were discovered out of sheer practical necessity during the Industrial Revolution, mostly because people really wanted to make steam engines better. Sadi Carnot kicked the whole thing off back in 1824 by looking at engine efficiency. Then Rudolf Clausius formulated the first and second laws around 1850. Walter Nernst brought us the third law in the early 1900s. But check out that last date. The most fundamental law of thermal equilibrium was recognized so incredibly late in the 1930s that instead of renumbering the first 3 laws, they just awkwardly stuck it at the very beginning and named it the Zeroth Law. Which perfectly sets up section 3, the 4 laws explained. So here is your bird's eye view of the whole shebang. The Zeroth Law governs thermal equilibrium. The first law is all about the conservation of energy. The second law drops the hammer and states that entropy always increases. And the third law establishes the absolute ultimate chilling limit of absolute zero. Let's break these down step by step, starting with our strangely named friend, the Zeroth Law. Now, the Zeroth Law sounds a bit like a weird riddle at first, but it is just pure, undeniable logic. It basically states that if 2 systems are each in thermal equilibrium with a third system, well, then they have to be in equilibrium with each other. Look at it this way. If a thermometer has the exact same temperature as a hot cup of tea, and that very same thermometer has the exact same temperature as a bowl of water, then the tea and the water absolutely must be the exact same temperature. So the big takeaway here?
This law is literally the entire reason thermometers even work and temperature scales can exist in the first place.
And that brings us to the first law. Energy simply cannot be created or destroyed. It can only be converted. Think of it exactly like your bank account. Depositing money into your account is like adding heat to a system. Spending that money is like the system going out and doing work. And your actual account balance, that's the system's internal energy. Money is never just magically created out of thin air or destroyed in this process. It only ever changes hands. The exact same thing goes for energy. The chemical energy inside a car's fuel becomes mechanical energy, heat, and sound. Absolutely no energy vanishes. It just changes form. Next up is the second law, and this one is a real game changer because it actually gives time an arrow. It states that the entropy of an isolated system never, ever decreases over time. It is the fundamental reason why natural processes only go in one direction. An ice cube melts in a warm room. A warm room doesn't naturally freeze a glass of water. A fresh cup of coffee cools down. It doesn't spontaneously suck heat from the cool air to get hotter. And crucially, it's why every single engine in existence loses some energy to heat and friction, which means a 100% perfectly efficient machine is a literal physical impossibility. Finally, we reach the third law. This law defines the absolute hard bottom of the temperature scale, absolute zero, or 0 Kelvin. At this incredibly frigid temperature, thermal energy is at the absolute lowest possible limit permitted by the laws of quantum mechanics. But here's the catch. You can never actually reach it. Scientists can get to tiny, microscopic fractions of a degree away from it, but extracting that absolute last tiny drop of thermal energy would require a totally impossible infinite number of steps.
All right, Section 4, the math and common mistakes.
Now, I know what you're probably thinking. This is a physics explainer. Where is the math? Don't panic. We're just going to translate these concepts into one super simple equation, and then I'll highlight some common traps you definitely want to avoid. The pure elegance of the first law is beautifully captured right here in this formula. Delta U equals Q minus W. The increase in a system's internal energy, that's our delta U, is equal to the heat added to the system, which is Q, minus the work done by the system, which is W. It perfectly, exactly mirrors that bank account analogy we used earlier. Let's just prove how ridiculously easy this math actually is. Suppose we add 500 joules of heat into our system. Boom, that's a 500 deposit. But then the system expands and does 200 joules of work pushing on its surroundings. That's a 200 expense. 500 minus 200 leaves us with exactly 300 joules of increased internal energy. It's just simple, straightforward conservation of energy in action. Okay, pop quiz time. Or, well, let's call them teacher pro tips on what absolutely not to do on an exam. First big mistake, confusing heat with internal energy. Remember, heat is the transfer, internal energy is what is actually stored inside the system. Second huge mistake, using Celsius in your equations when you absolutely should be using Kelvin, the absolute scale. And the third mistake, which straight up violates the second law, assuming any real-world engine can ever be 100% efficient. It is a thermodynamic impossibility, so don't fall for it.
And finally, Section 5, Thermodynamics in the Real World.
So we've nailed down the laws and the math. But as your resident physics guide, I've got to answer the classic student question. Why does this actually matter in the real world? Well, it's all about scale. On the left, we've got massive mechanical heat engines, car engines, jet engines, industrial turbines, all built entirely around maximizing the first and second laws to convert heat into raw mechanical work. But look over on the right. The human body is also an open thermodynamic system. You take in chemical energy in the form of food, and your cells brilliantly convert it into muscle movement, body heat, and electrical signals in your brain. Whether we are talking about heavy steel pistons or living human tissue, the rules of energy transfer are exactly the same. Let's do a quick rapid-fire rundown here. Without these laws, we couldn't even build refrigerators or air conditioners, which actually use external work to artificially pump heat from a cold region to a warm one. Power plants, whether they are solar, nuclear, or geothermal, all completely rely on thermodynamic cycles to generate the electricity powering your home. Heck, even the device you're watching this explainer on depends on thermodynamics. Engineers have to design CPU cooling systems and heat sinks specifically to manage the heat generated by your electronics so your phone doesn't literally melt in your hands. We have covered a ton of ground today, but I want to leave you with one final, kind of mind-bending thought. If the second law of thermodynamics dictates that the entropy, the energy dispersal of the entire isolated universe, is always increasing, always spreading out, what does that actually mean for the ultimate fate of all energy, heat, and life itself?
If absolutely everything is slowly, inevitably evening out into a uniform state of maximum entropy, what happens when there are simply no more temperature differences left anywhere to do work? I will let you ponder that incredibly deep, chilling question until our next explainer. Keep wondering, keep learning, and class dismissed.